Let me get started. My name is Sergey Levin. I'm an assistant professor at UC Berkeley and also a part-time research scientist at Google Brain. And today I'm going to tell you about deep reinforcement learning and meta-learning, how we can build flexible and adaptable machine intelligence. So first, let me introduce myself by way of a few videos of some experiments. So in my lab at UC Berkeley, what we work on are algorithms for machine learning and reinforcement learning. We develop algorithms that can enable autonomous machines to make decisions, to act in the world, and then we extend these methods to experiment with them on real-world robotic platforms. So we work on robotics, but we kind of see robotics as actually a lens through which we can study how we can develop better autonomous machines. So while a lot of the things that I will talk about actually in today's talk will pertain to robotic systems, the story is really a story about machines that can make decisions. Robots are simply the most physical manifestation of that. They're machines that observe something about the world, make a decision, and then act on the world using their actuators. But in the same way, you can imagine a robot-like machine could be something on the internet that observes users interacting with it and makes a decision, a smart power grid that observes telemetry and decides how to allocate storage and capacity and so on. So I'll talk about robots, but keep in mind the story pertains to a much wider range of problem settings. And then the story that I'm going to discuss deals with deep learning and decision making. Because if we want intelligent systems, they need to be able to understand complex, unstructured open world environments, and they need to be able to act in those environments. And deep learning is the tool that allows us to handle unstructured environments. Deep learning is very good at this for a number of reasons. So the basic idea behind deep learning, it's actually a very simple idea, is that we're going to train a sequence of layers of representation directly end-to-end on a task that we want to solve. So if we want to solve the task of image recognition, maybe we want to recognize different species of animals in pictures, we're going to train not just a single layer classifier, but actually multiple layers of representation end-to-end to solve the task that we want. And this addresses two big problems in machine learning. The first one is that we don't need to manually design representations, and the second one is that all of the representations are actually optimized for the task at hand. And we've seen a lot of very impressive successes in the world of deep learning for things like recognizing objects in images, translating text, recognizing human speech, and so forth. But deep learning by itself doesn't give us a formalism for making decisions. Deep learning is about solving mapping problems, mapping from images to labels, from sequences to text, and so on. If we want to reason about how we can build intelligent machines that can make decisions, that can bring about desired outcomes, then we need to also introduce a mathematical formalism for decision making. And that's what reinforcement learning provides us with. It provides us with a mathematical formalism for behavior. Reinforcement learning models an agent interacting with the world where the agent makes decisions that we call actions, and the world produces consequences, observations, and rewards. And crucially, in a reinforcement learning setting, the agent isn't told in advance, these are the outputs, these are the decisions you should make in response to these observations. The agent is told that you should maximize your reward, maximize these particular desirable outcomes, and then the agent has to figure out on its own which actions to take to bring about those outcomes. So the idea of combining deep learning with reinforcement learning is actually a very old idea. It actually predates the term deep learning. So one of the earliest learning-based systems that could defeat expert human players at a board game was actually built in the mid-90s, the TD Gammon system, which used neural networks as function approximators for a reinforcement learning algorithm to play backgammon. And the basic principles behind AlphaGo, which was in 2016, are actually at a very high level very similar. Both of them are based on value function estimation, where the value function is represented with deep neural networks and trained with reinforcement learning. And we've seen deep reinforcement learning algorithms applied across a range of other domains like simulated locomotion for robots, basic manipulation tasks, playing Atari games, and so on. But if we look at a lot of these tasks, one of the things that we might notice actually about all of them is that they all operate in closed world environments, in the sense that the world of backgammon or Go, or even these simple robotic manipulation tasks, is constrained in the sense that extraneous events never creep in. Unexpected things don't really happen. You don't have to worry about somebody spilling coffee on the Go board or the Atari game suddenly turning into a different game or something like that. They're closed world environments with known rules. And that's in very stark contrast to what we get when we try to run machine learning methods in real world settings. Settings like recognizing objects in images that are, for example, randomly sampled from Flickr. So real world environments, they're open world environments, they're unstructured environments, and they demand a very high degree of generalization from machine learning systems. And this is something that actually a lot of the past successes in deep reinforcement learning haven't really explored in depth, because they focused on closed world environments with known, well-understood rules. So current reinforcement learning methods look at these kind of closed world environments, and the way that they operate is through an iterative procedure, where the agent interacts with the world, collects a little bit of data, uses that data to improve its model or policy, then interacts with the world again, throws out the data that it collected, gets new data, uses it to improve its model or policy again, and so on and so forth, which is a very logical way to get progressively better at doing a task. But it's very limiting when you start thinking about generalization, because generalization demands large data sets that can be used to learn behaviors that actually generalize. So if you're, for example, interacting with a single Atari game, like the Space Invaders game there in the top left corner, perhaps it's fine if you can only handle a universe that consists of yellow aliens and a little green spaceship. But in reality, there's a lot more diversity, there's a lot more visual complexity, and that means that generalization requires larger data sets. And if you imagine extending this scheme in reinforcement learning to environments with large data sets where generalization is actually important, then you end up actually with a picture that doesn't look so practical. If you imagine, for example, collecting an ImageNet-sized data set every time you want to modify the behavioral strategy of your agent, then you can't really throw out that data and recollect it all over again every time you change your policy. So if you have, let's say, an autonomous car that's learning to drive on any city street in the world, you can't really have it drive, collect data, modify its policy, throw out all of that data, and then recollect it all over again just to modify the policy another time. You'd like to be able to reuse past experience to generalize. So how can we generalize effectively without being able to train on large data sets? Well, the answer is that we can't. We have to develop reinforcement learning algorithms that can handle large data sets of past experience rather than relying slavishly on this kind of iterative loop where you throw out your experience each time. So what we need is algorithms for scalable off-policy reinforcement learning. Off-policy means that the algorithm can use not just the latest data collected with the latest policy, but also past data from other policies, from other sources. Data sets that can actually be used to learn behaviors that generalize in whatever domain we care about. I'll talk about the domain of robotics, but similar lessons I think will apply equally to other domains. And then we need to also be able to transfer from prior tasks to accelerate learning of new tasks. So if, for example, we have a robot that's learning some set of behaviors, maybe it's a household robot, it needs to do some chores, do the yard work, do the laundry, and make the dinner, well, perhaps every time you want that robot to learn a new task that you would like for it to do in your home, you don't want it to start from scratch. You want it to be able to reuse past experience that it has. And this implicates both the off-policy reinforcement learning and the ability to transfer. So I'll talk about each of these topics in today's talk. But the high-level idea behind actually all of the things that I'll discuss is large-scale off-policy reinforcement learning. Reinforcement learning algorithms that can generalize effectively from large amounts of data that was not necessarily collected with the latest policy. So the scheme here is that instead of this iterative loop where data is recollected every time, you have an agent that has interacted with the world in the past, collected data for a variety of tasks in a variety of situations. It'll use that data to train a policy, a model, or a value function for many epochs such that it generalizes effectively because it has been trained on a large amount of highly varied data. And then occasionally it will go back into the world and collect a little bit more data to figure out those corner cases, those hard to discern situations where a little bit of additional experience is necessary. But the bulk of the generalization comes from this stuff over here, from all those past interactions, and then a little bit of fine-tuning comes from the on-policy interaction with the world. So concretely, what I'll talk about are three main topics. First, I'll discuss off-policy model-based reinforcement learning algorithms. Model-based reinforcement learning is something that perhaps doesn't come up in the news quite as much, but it's actually a very practical and very effective way to learn skills using off-policy data based on prediction. Then I'm going to talk about off-policy model-free reinforcement learning algorithms and describe an example in robotic learning where we've done some experiments with this. And then I'll talk about improving efficiency through meta-learning. And that's really going to touch on this last point about transfer, where I'll discuss how past experience of learning other tasks can be used to accelerate the learning of new tasks. So let's start with the model-based reinforcement learning topic. Model-based reinforcement learning focuses on learning to predict the future and then using the predictive model to act. Acting with a predictive model essentially amounts to planning. It's actually a very well understood topic that people have known about for decades. Most of the trickiness in model-based reinforcement learning is in learning to predict. So the idea is that you have an agent. That agent has interacted with the world and collected a large body of past experience, just like I described before. And we can add a little bit of mathematical notation just to make this concrete. The past experience consists of transitions. State observations S, actions that the agent took A, and the next observation that it got, which was S prime. And now we're going to use that data to learn how to predict the future. We're going to train a model, a large neural network, that predicts the next state given the current state in action. And that is going to allow us to then be able to act. We can train this model for many epochs on past state, and then we can use it to act by using any planning method. So in a robotics context, the way that this might look is that you have robots that interact with the world. They collect data. The data is used to train the model. And then when the robot is asked to actually do something, it's going to imagine what the consequences of different action sequences might be according to its learned model, and then execute the actions that lead to the user-specified outcome. So the user says, I want you to move this object over here. The robot queries its model with different action sequences until it finds one that produces that outcome, and then it executes it. So the work I'm going to describe was really led largely by these three PhD students, Frederick Ebert, Chelsea Finn, and Alex Lee. And if you're interested, these papers go into more detail about what I'm going to cover. So the first stage in these algorithms is to collect data. And we can collect data in a number of different ways. You can collect data from demonstrations, from past things that the robot has done. But we're actually going to go with the simplest way of collecting data, kind of inspired by, in part by what children do. You know, if you have a small child, maybe the child plays around with objects in its environment. It's not really trying to accomplish any particular goal. But in the process of interacting with its environment and trying different things, the child can build up a mental model of how the world works, a sort of intuitive model of physics. And our robots are doing a very, very simple version of the same basic principle. They're going to play with objects in the world by interacting with them randomly. Here, they're not trying to accomplish any goal. They're just moving the arm through random motions. But as they do this, they're recording the observations from the camera and the actions that they executed. And then they can use this data to learn to predict future outcomes of their actions. And they're going to learn to predict directly in the space of observations because that's something that's always available to them. That doesn't make any assumptions about whether the objects are rigid or deformable, how many objects there are, or anything like that. We'll just directly predict the pixels. So we're going to take all the data that these robots have collected and use it to train a model. In this case, it's a recurrent convolutional model that's going to predict future images, conditioned on past images, and the actions that the robot is considering executing. So what you're seeing on this slide in the two rows, the two rows show different environments, but every column is a different prediction for that same environment. So in the first column, in the first row, all of those images are predictions starting from the same image, but for different action sequences. And in the second row, there's another image, and again, each column is a different prediction starting from that same image for a different action sequence. So you can see that the predictions get a little bit blurry, but they kind of capture the basic physical properties of the world, that when the arm touches something, that object will move. If the object collides with another object, that other object will move. So in some sense, the model has captured a kind of intuitive notion of physics, collisions, inertia, and so on, to the level that it can actually use it to do things in the world. And then we can give the robot a task. There are a number of different ways to give the robot a task when it's using predictive models to act. Here, the way that we're going to give the robot a task is simply by clicking on the screen. We're going to click on one point, that's the red diamond there, to say, move this object. And then we'll click on a different point, indicated with the green diamond, say, move this object to this location. That's just a way to interact with a system. You can imagine any other way of interacting with it. Maybe we can do some scribbles or run some object detector, whatever. Something that will actually tell it what our intention is, what we want it to do. Keep in mind that the robot is not actually programmed to know anything about objects a priori, so it doesn't know that that red diamond is actually on top of a rigid object called a stapler. All it sees is image pixels. Anything that it knows about objects, it has to figure out from the data by building those predictive models. So once we've specified the task like this, the robot can imagine different outcomes for different action sequences. So what you see on the left side of the screen is a video that is predicted by the model for a particular sequence of actions. The heat map at the bottom shows the predictions for this action sequence just for the movement of that red diamond. And it's predicting that indeed, if it executes this action sequence, that point will move to the right in the direction of the user-specified goal. Now, in reality, the model has to imagine many possible outcomes of many possible actions and then choose the best one. And the one I'm showing here just happened to be the one that it chose. So once it chooses a sequence of actions, then it can actually execute them in the real world, and then the robot can perform the task. Now, in reality, when the robot performs the task, it's actually continuously replanning. So if the real world does something different than what the model predicted, it actually replans a new sequence of actions to make sure that it can correct mistakes. Here's another example. Here we ask the robot to move an oven mitt to a particular location. The nice thing about this kind of approach is because it reasons directly at the level of image pixels, it doesn't actually make any assumptions about whether the objects in the environment are rigid or flexible or solid or liquid or anything like that. It directly deals with the world the way it actually is. It's a data-driven approach. So that means that it can move the soft deformable oven mitt without really any confusion. OK, so that's model-based reinforcement learning. Now, model-based reinforcement learning has a number of advantages. For example, you can train one model that understands something about the physics of the world and then use that one model to perform many different tasks. But it also has some disadvantages, because training a very effective model really requires understanding the world in depth, understanding everything that could happen, all the variability of physics and so on. If we want a system that's a little more focused, maybe we don't care about doing lots of tasks, but we want to do one task really, really well, then we can employ a model-free method that doesn't attempt to predict everything that will happen, but cares mainly about a single desired outcome. So that single desired outcome is typically specified with what we call a reward function. So the story in off-policy model-free reinforcement learning will be that, again, you have an agent that has interacted with the world. It has collected a large data set of past interactions. Again, those past interactions consist of states, actions, and next states. But now there's going to be a task reward. There's going to be some additional signal that tells the agent whether it's doing the task well or poorly. Crucially, this reward is only a function of a current state in action. But the goal of the agent is to maximize that reward over a temporal window, over potentially a large temporal window. So it can't just greedily take the action that will give it the best reward right now. It might need to do things that currently seem unrewarding, but will become rewarding later on. And that's the main challenge in these kind of reinforcement learning settings, that you have to actually reason about the future. But otherwise, it's going to be the same story, that we're going to train for many epochs on that off-policy data to figure out how to maximize the reward, and occasionally go back out and interact with the world a little bit more to collect a little bit more experience. So to figure out how we can do off-policy model-free reinforcement learning, we need to first actually write down the reinforcement learning objective. The reinforcement learning objective is actually quite simple. It's simply to maximize the total reward over a temporal window, what we call the horizon. So the sum of rewards from time step 1 to capital T, where capital T is the length of your horizon. You can also do this for infinite horizon when t goes to infinity. I won't go into that here, but it's actually pretty straightforward. A very useful object for thinking about how to maximize this objective is what's called the Q function. The Q function simply tells us if you are in a particular state and you execute a particular action and then follow your policy, what will be your total reward? So the objective is just the expectation of the Q function in the first time step. And there's a really interesting property about these Q functions, which is that whatever policy you learn this Q function for, you can always improve that policy by changing it to one that takes the action that is the argmax of the Q function with probability 1 and all other actions with probability 0. So if you train a Q function for some policy, and then you switch to a different policy that is greedy with respect to the Q function, that always takes the action that the Q function thinks is best, that new policy will be better than your old policy. So that suggests a particular way of optimizing behavior with Q functions. If you can train a Q function by repeatedly fitting a Q function to a policy and then changing the policy to be the one that greedily maximizes that Q function, you will actually recover eventually the optimal policy. And you can actually show that's equivalent to finding a Q function that satisfies this equation. The Q function that is equal to the current reward plus the max over the Q function at the next state. So it's a nice mathematical identity, but we can actually use this as the basis for a learning algorithm. And this learning algorithm, it's actually still going to solve a prediction problem, just a different prediction problem. Instead of predicting future states, it'll actually predict future rewards, which is what the Q function is. The Q function is telling you what are the rewards you'll receive in the future. So we're still predicting, we're just predicting something else. We're predicting something more focused, which is the reward signal. And the nice thing is that because you're still learning to predict, you can do this with off-policy data. You don't actually need data from any particular policy. You'll just enforce this equation on all the data you've collected. So how do you solve for the Q function? Well, you need to enforce this equation on all of your transitions. So you don't need on-policy data to do this. You can get data from any policy you want, although the closer it is to your current policy, the better. And the off-policy Q-learning algorithm basically works like this. You collect some data using whatever exploration policy you want, or even many different exploration policies. You add it to some buffer where you're going to store it. Then you have an inner loop where you're going to sample a batch of data from this buffer, minimize the difference between the left-hand side and the right-hand side of that equation on that batch, and then repeat this some number of times. And occasionally you go back in and collect more data. So we can illustrate this graphically. You have your environment. You've interacted with the environment and collected these transitions and their rewards. You put them in your buffer. And then you have a separate process that goes through this buffer, pulls out transitions, minimizes the difference between the left-hand side and the right-hand side of that equation to give you a better Q function. And occasionally there's some other process that uses your latest Q function perhaps, or some other exploration strategy to go back into the world and collect more data. And you can actually implement all this asynchronously, and that actually ends up working quite well. So let me tell you about an experiment that we did to study this algorithm in a large-scale robotics setting that actually requires generalization. This appears in a paper called Qt-opt. And the setup in this work is the following, that you have a number of robots that are collecting data. So you can imagine maybe these robots are deployed in a warehouse or a factory. Here they're deployed in a lab. They're collecting the data continuously. And we have a buffer of all of the previous transitions that we observed. The experiment itself might take several months, so maybe some of the data in the buffer is old, some of it is new. The robots are continuously adding data to that buffer. So then what we're going to do is we're going to have a set of training buffers that we'll actually use for training our Q function. Part of the data there is loaded from disk, from these stored transitions. Part of it is loaded from what the robots are currently collecting and also saved to disk for later use. And remember that our goal is to minimize the difference between the left-hand side and the right-hand side of that Q function equation. So what we need to do is we need to actually compute the right-hand side. So for that, we'll have a set of Bellman updater workers that will crawl over this buffer, pull in transitions, compute the right-hand side, the R plus the max of the next Q, and they'll push that back to a labeled buffer. So the labeled buffer now has the state, the action, and the right-hand side of this equation. And then we can have a separate worker that actually pulls from that labeled buffer and minimizes the difference between the Q and these target values, the right-hand side equations that were computed by the Bellman updaters. So this is a kind of a large-scale architecture for optimizing Q functions from off-policy data and simultaneously data that's collected live from the system. And here it's collected from robots, but again, you can imagine this happening with any other kind of system that has to interact with an environment and perceive the world through some sort of sensory inputs. So we applied this approach to robotic grasping. Robotic grasping is kind of a nice problem because the reward function is very clear. You either picked something up or you didn't. So that makes it a nice experimental platform. We trained it on several thousand objects in the real world. The experiment took about 3 months. So about 1,000 training objects, about 600,000 training grasp attempts. And the whole thing was, it's running autonomously, right? So the robots can pick things up, drop them back in, and so on. And we train a network with about 1.2 million parameters. So this is quite a bit bigger than what is typically done in deep reinforcement learning, but that's because now we actually want this thing to generalize to new objects that it's never seen before. So we don't want it to be restricted to the closed world of only those objects that it was trained on. We want to actually see real generalization from this. But the only kind of grasp-specific feature here is actually just the reward. So the system, you can imagine applying the same general approach to other problems. You just need a reward function. So the quantitative results for this, for those of you that are actually interested in robotic grasping, they're actually pretty good. So we tested this on a range of very difficult objects, small, big things, transparent things, et cetera. And it gets about 96% accuracy, which is pretty decent. Like if you want this thing working like a warehouse, that's a pretty good success rate. But what's more interesting for me, actually, is the qualitative behaviors that we see emerging from this. Because this was a system that was not actually programmed to grasp objects in a particular way. It actually had to figure out how to grasp them, which meant that it learned a variety of strategies that allowed it to pick up objects more effectively. So one thing it learned is the singulation behavior. If it sees objects that are kind of clumped together like this puzzle, it'll actually separate them out before picking up the individual pieces because it learned through experience that that's something that actually gets it a higher probability of success. One of the things that you'll see in a second is that sometimes this thing actually makes mistakes. But one thing it learned is that when it closes the gripper, it can actually watch whether the object stays in the gripper or not. And if it doesn't, then it can reopen it. So here it makes a little mistake. It slips out and says, oh, no, there's nothing there. Let me just go in and try again. We can further actually experiment with this thing. We can perturb it a little bit and see how it responds. So there it has this behavior where it slipped out of the gripper again. Once it's done with this puzzle, there'll be another example where we're going to mess with it a little bit. Okay, so there's the puzzle. And now we're going to give it some difficult objects to pick up. So some of these are very large and awkwardly shaped. And then we're going to have someone go in and mess with it a little bit to see whether it can recover successfully. And you can see that it actually grasps the object at the center of mass, changes its grip based on whether things are working or not, and so on. The tennis ball is also a pretty difficult one because that one tends to slip out of the gripper. And even when it doesn't, then the mischievous experimenter goes in and forces it to slip out. But then it chases after it and actually still succeeds. That little clothes hook is also a really difficult object to deal with because it's kind of small and awkwardly shaped. So here it's going to have a few false starts, but then it figures out that, OK, I didn't actually pick it up. Let me go in again. That didn't work. Let me go in again. And eventually it'll actually get it. And this kind of trial and error sort of thing is actually pretty important for realistic situations where you'll never really succeed on the first try. OK, so far I talked about how we can use large amounts of off-policy data to learn policies that can generalize effectively, that can generalize to new tasks in the case of the model-based RL, or to new objects they've never seen before in the case of the model-free algorithm. But one of the things that we'd like to do is we'd like to also be able to use past experience to learn how to learn new tasks more quickly. So maybe there is actually some additional learning that needs to happen. Maybe you don't get generalization in zero shot right away, but perhaps you can still use your past experience so that that new learning on the new task goes more quickly. So one of the ways that we can formalize this problem of learning to accelerate learning is actually by redefining the notion of a data set or a data point. So while we can think of the meta-learning process, this learning to learn, as some kind of mysterious and complicated thing, in reality, if we change our definition of what makes a data point, things actually become much simpler. So I'm going to illustrate this idea with just regular supervised learning, actually image recognition, but the same ideas apply to reinforcement learning as well. This is a figure borrowed from a paper by Ravi and La Rochelle, where they're illustrating this idea of redefining the notion of a data point. So you could say that if you're learning to learn, what you really have to do is you have to create a data set that itself consists of little data sets. So what we call meta-training, that's the meta-training data set, and every data point in that data set is itself a little data set. So perhaps you'd like to recognize new classes of objects and images, take all the classes of objects that you have, chop them up into little training sets and little test sets. So each training set maybe has 5 pictures. Each test set has 2 pictures, which are of the same class as in the training data. And then you're going to train your model so that when it sees the little training set, it does well on its corresponding test set. So if it sees, like in that top row, the bird, the mushroom, the dog, the person, and the piano, it should become good at distinguishing those 5 classes, so then it should do a good job on the test dog and the test piano. And you have many, many of these little training sets inside the meta-training set. And then at meta-test time, you give your model a little training set with new classes that it has never seen before. So that has whatever that is, a cat, a dog, a lion, some kind of worm. Those are things that were never seen during meta-training, but because the model learned to ingest little training sets and do well in their corresponding test sets, now can ingest this new little training set with objects that it's never seen before and do well in the corresponding test set. So how do we actually do this? How do we build models that can solve this kind of problem? So one of the ways that we can formalize this mathematically is we can start by thinking about supervised learning and then turn supervised learning into supervised meta-learning. So a regular supervised learning problem basically learns a function that goes from x to y, right? So maybe x is your input, like your image, and y is your output, which maybe is the label. Supervised meta-learning learns a function that maps from a data set, dtrain, and x to the label y. So maybe your supervised meta-learn needs to classify that white dog in the first test set. What it needs to do is it needs to ingest the images and the labels for the corresponding training set and the image of the white dog and output y, which is the label that says dog. So how do you build a model that can take in this whole training set dtrain? Well, there are a few different choices. And in fact, a lot of research in meta-learning has focused on basically exploring different choices for that architecture. One very simple choice is to use a recurrent neural network, the same kind of model that you would use to ingest a sequence. So you have a sequence model that reads in x1, y1 in the training set, x2, y2 in the training set, et cetera, et cetera, et cetera. Then it reads in the test image, and then it spits out the test label. And it's just trained with supervised learning to do this using the meta-training set. Now, of course, a very simple, straightforward recurrent neural network architecture might not be the best choice. And in fact, a lot of past work has studied different representations, different neural network architectures for solving this problem. So memory-augmented neural networks, networks that have kind of a non-parametric flavor to them, like in the matching networks paper, and so on and so on, prototypical networks. There are basically many different neural network architecture designs for trying to address this. And there are many, many others. addressing the problem by designing better and better architectures will allow us to make progress. But a few years back, we thought about this a little bit, and we wondered, well, is this really the best way? Is it really about engineering the right neural network, or is there something more basic that we can do to come up with a simpler meta-learning procedure? So if we step back a little bit, one of the things we can think about is, well, what are things that are like meta-learning but simpler that have worked really, really well in the past? And one thing that has worked really, really well, at least in computer vision, is pre-training. So if you take a really big data set like ImageNet, and you train a convolutional neural network on ImageNet to recognize object classes, and then you take the features from that network, and then you fine-tune on a new task, like maybe recognizing parts of a bird, you'll actually get very good results, because something about what that model learned from ImageNet contains good visual features. Now, this is not really a meta-learning algorithm. It's not explicitly trying to learn how to learn. It just so happened that in the process of learning to classify ImageNet, it got good at doing other visual tasks. But what if we take this idea and we try to make it explicit? What if we actually ask the model to learn how to learn during this pre-training phase? So is pre-training a type of meta-learning? And can we actually ask the model to give us better features that will make it faster on a new task without necessarily getting lucky and picking the right data set like ImageNet? So this is what I'm going to discuss is a work called model-agnostic meta-learning. This is work that was led by a PhD student named Chelsea Finn. And the idea here is that you're going to have the same setup. You're going to have the meta-training set and the meta-test set. But now we're not going to use a big recurrent neural network. We're actually going to use exactly the same type of network as you would use for regular image recognition or supervised learning or reinforceable learning or whatever. And we're going to take into account the fact that when we get a new task, we're going to try to solve that task by fine-tuning. Now, what is fine-tuning? Fine-tuning is training your model with gradient descent. So we're going to optimize our model such that when you fine-tune it on a new task, it does well. So how do you fine-tune on a new task? Well, you compute the gradient of your model, and this expression shows the loss. So this is the loss of the parameters of your model theta on a new data set, dtrain I. And you compute the gradient, and then you subtract the gradient times the learning rate from your parameter vector. And you might do this multiple times, but I'm just showing it once just for notational clarity. So what we want is we want a model such that when you do this, you get a good result. And in general, you can take more than one gradient step. So what you can do is you can say, well, let's have another loss function outside of this thing that says, on the test set, you should get good performance after taking a gradient step on the training set. So we know you're going to fine-tune, so we'll optimize your network so that it does well after fine-tuning. And you can actually compute derivatives through this kind of second-order loss function and train a model with parameter vectors that are good for fine-tuning. So this outer loss is the meta loss for task I. It says after you've adapted on the training set for task I, you should do well on the test set for task I. And then you sum this over all of your meta-training tasks, and that's your meta-gradient. So once you've trained using this meta-gradient, then when you see a new task at meta-test time that you've never seen before, all you do is regular fine-tuning, but because the model was trained for that fine-tuning to work, it'll actually get good performance. So let me illustrate kind of a little qualitative result with a reinforcement learning example. The same exact idea applies to reinforcement learning. And what we're going to do here is we're going to teach this little quadrupedal robot to run in different directions. So what I'm going to first show you is the behavior of the policy after it has been meta-trained, but before it's adapted to any task. So this is not the performance on an actual task. This is the policy that is ready to adapt. This is the policy that has been meta-trained. And what it does is actually very intuitive. It actually runs in place. Right? It knows that all the tasks involve running to different directions, so it's going to run in place because it's ready to go. Now it's going to observe reward. It's going to take one iteration of policy gradient, of reinforcement learning, and then it can adapt to run in a particular direction. For example, if the reward was to run forward, then after one step, it switches to forward running. If the reward was to run backward, then after one step, it switches to backward running. We can, of course, also run this on supervised learning problems, image recognition, and so on. One of the nice things about this approach is because it's actually fairly simple and can be applied to any standard neural network architecture that you can use for regular supervised learning, there's been quite a bit of follow-up work that extends on the results. And actually, the results for model-agnostic meta-learning on supervised learning tasks keep getting better and better. So one standard benchmark that's actually used in the few-shot learning community is something called mini ImageNet. It's a smaller version of ImageNet adapted for few-shot learning, where you see new classes that you've never seen before at meta-test time. Our original result on mini ImageNet for 5-shot, 5-way classification was 63%, which at the time was pretty good, but today's actually, it's wildly obsolete. It's not good anymore. But actually, other papers since then have basically built on the same general framework, and the results for MAML keep getting better. The latest from Kim et al. In 2018 actually used a neural architecture search algorithm to design a better feed-forward architecture, and then ran MAML on top of that and got more than a 10% increase. So it's a fairly extensible approach that quite a few works have followed up on. OK, the last thing I actually want to touch on in regard to meta-learning is that while it sounds like a very appealing prospect, there are some problems with meta-learning. And in the same way that regular learning algorithms can overfit, meta-learning algorithms can meta-overfit, which sounds a little funny at first, but let me explain what I mean by that. So meta-learning requires us to define these task distributions. So someone has to create all those training sets in the meta-training set. So for example, if we want the little quadrupedal robot to run in different directions, someone has to specify that during meta-training, learn to run this way, learn to run that way, learn to run that way, and so on and so on and so on. And then maybe after you've trained it, it can run in place, and then after you adapt it, it can run in the right direction, and so on. But when there are too few meta-training tasks, when the distribution of tasks available during meta-training is not representative of what you'll see at meta-test time, you can meta-overfit, which means that the model is good at adapting to the kinds of tasks it saw at meta-training time, but not necessarily good at adapting to weird tasks that you might ask it to do at meta-test time. And that can be a big problem. So in a sense, specifying the task distribution is one of the most important things, especially for meta-reinforcement learning. So while meta-learning removes the need to design better algorithms for fast adaptation in some sense because it learns those procedures, it sort of offloads that burden onto the person designing the tasks, because now it says, OK, now you have to give me the tasks that will allow me to meta-learn this thing. So can we automate the process of task design as well? One of the things that we've studied recently is automating task proposals for meta-reinforcement learning. So a general recipe for unsupervised meta-reinforcement learning is that you're going to have some kind of task proposal that's going to propose different random tasks for you to practice. Ideally, as wide of a distribution of tasks as possible. You'll practice those tasks, and as a result, become good at adapting to other new tasks that you haven't seen before. And if that task distribution that's automatically generated is broad and diverse enough, then you might actually build a model that can adapt to highly varied tasks specified by a person at meta-test time. And there are actually quite a few ways that you can generate those task proposals. In fact, very simple ways of generating task proposals can actually work decently well. One of the simplest things we've tried is simply random task proposals, where you initialize a random classifier, and then you ask your policy to maximize the probability of different classes in that classifier. So the classifier looks at the state, it spits out a categorical distribution over, let's say, 20 different classes, and each class is a task. And then you can practice those different tasks. It's a very naive method, but it actually already gives you improvement over running reinforcement learning from scratch. A better approach is to use what are called diversity-driven proposals. So here, you still have your classifier, but now the classifier will not actually be random. It'll actually be trained. The idea is that the policy and the classifier will actually collude. So the classifier will try to classify the state, and the policy will try to visit the states that make it easier for the classifier to guess. So you can imagine this as there are different regions in state space, and the policy is trying to go to different regions that are as discernible from each other as possible. And that results in tasks that achieve wider coverage. So again, the reward is to maximize the probability for the classifier, and the classifier is trying to do as good of a job as possible of discriminating the different classes. So if you just run these diversity-driven proposals on simple kind of benchmark reinforcement learning tasks, you already get actually pretty diverse behavior. For this little half-cheetah thing, sometimes it runs backwards, sometimes forward, sometimes it makes a backflip, and so on. So it's doing different things, not necessarily things that are achieving any concrete user-specified goal, but things that are diverse enough that when meta trains on these, it'll actually learn to do lots of different stuff. And we can quantitatively compare learning curves for learning from scratch versus learning from these unsupervised tasks. So what you see here, the red curve shows what happens when you learn entirely from scratch for a new task at meta-test time. The blue curve shows what happens when you learn after meta-training on random task proposals. And the green curve shows what happens when you train on diversity-driven task proposals. So the green one is always better than the red. The blue one is sometimes better. So even the random proposals actually sometimes cause you to learn useful initializations that can then be fine-tuned much more efficiently for new tasks. OK, so I think at this point I'm almost out of time. There's a robotics application for meta-learning that I have in the slides for those of you that are interested. But at this point, I think I'll wrap up and take some questions. So but just to summarize the main point, I talked about how reinforcement learning can be extended to a setting where generalization is sort of a first-class citizen. In order to get there, we need to think about off-policy reinforcement learning, algorithms for scalable off-policy reinforcement learning, data sets that can be used to learn behaviors that generalize and transfer to accelerate learning of new tasks. All right, thank you very much, and I'd be happy to take any questions. I think there's a microphone in front here if anyone wants to come up to ask questions. Yeah. I can just repeat the question. I can hear you. Right, so the question was, where do you see reinforcement learning being applied besides robotics? So essentially, any situation that involves an agent interacting with an environment where it observes some complex observations, has to choose actions, has to reason about long-term consequences of those actions, are settings where reinforcement learning can be applied. Robotics just happens to be a very sort of physically visceral example, but you can imagine the same principle at work if you have, let's say, a system that's interacting with users on the internet, some kind of financial application, if you have an autonomous car, basically anything where there's sensory readings going in, actions going out, and your goal is to maximize some long-term metric of performance. Now, where can you do that practically? That's a more complex question. And I think that actually in many settings that we care about in practice, those are settings where this iterative interaction process is actually very costly or very expensive. And that's where I think off-policy reinforcement learning becomes so important, because off-policy reinforcement learning can in principle use large amounts of historical data to get started without relying on this kind of a blind trial and error mechanism right from the start.
Okay, so there's an OpenAI article talk about how to combine the supervised learning and unsupervised learning in the NLP setting, right?
Yep.
So do you see some of the parallel for motion control?
So that's a really good question. What does unsupervised learning do at a basic level? Unsupervised learning is something that that deep learning researchers have been after for a really long time. Unsupervised learning is very appealing because in principle it can use data that is not labeled. Unlabeled data is very plentiful, so it's very desirable to use unlabeled data. The trouble with unsupervised learning is that it's a very underspecified problem. So you have this unlabeled data. What do you do about it? Well, maybe you're going to figure out something about the structure in there. Maybe you figure out that, well, dogs tend to stand on top of the ground rather than flying around, whereas birds can fly. So therefore, if I see something flying, it's probably a bird. Like there's this kind of structure that you can recover in the world, but there's a lot of structure in the world. So how do you know what to recover? Meta-learning, in some sense, sidesteps this issue by saying, well, we're going to use data that is labeled, but it's labeled for a different task. So okay, that makes it obviously a lot easier, but now you have to actually get this task distribution. And then unsupervised meta-learning says, okay, you're going to do that thing where you try to recover structure, but you're not going to rely on the structure itself. You're actually going to just use that structure to propose tasks, labeled supervised tasks, just with fake labels, that you can then practice solving so that you get better at solving new tasks. So it still has this problem potentially of building up on top of nothing, like the structure has to come from somewhere, but the problem that it's solving in that inner loop, the meta-learning problem, is using supervision, just fake supervision. So maybe for that reason, it might kind of succeed where unsupervised learning has proven to be very difficult.
Okay, so the other question is that for the simulation generation, what kind of simulators you guys use? Did you build yourself or?
Yeah, so for a lot of the experiments that I showed, actually, all of the robotic experiments, the ones that were in the real world, were trained directly on real world robots. We use simulation for just prototyping our algorithms. We also do some work on simulation to real world transfer, which I didn't talk about in this presentation. But a lot of what we do is built on the Majoko simulator, not for any good reasons, simply because it's a very easy simulator to use. Other very good simulation packages, if you're interested in robotics, are Bullet. That's a pretty good one. There's a few others that are a little bit more popular kind of in industry, but that's maybe a discussion we better have offline.
Yeah, I have a question about federated learning, because I saw one of your slides had a snippet of federated learning. So the problem is this. I work for HP, and say for different predictive and prescriptive maintenance, the situations are different between the manufacturing environment, right? And there we work on very deterministic model, which has a okay performance. Now, the problem is, of course, how do we transfer those learnings around? So what sort of approaches have been taken in real-world implementations of reinforcement learning for federated learning for those things? Is this ensemble, or how do you suggest us?
Right. So you're referring to like the distributed RL architecture I discussed for the grasping robot example. Yes. So the system there is still actually training just a single model.
Okay.
The training process itself is distributed, but but there's actually only one vector of model parameters. They're just accumulated on a parameter server in the same way as in any kind of classic asynchronous SGD application. You could have separate models, and in fact, we have actually done work that I didn't cover in this talk on training multiple different models and then regularizing them so that they don't stray too far from each other. And there's all sorts of things you can do there that are kind of inspired by dual decomposition. I don't think there's really anything that is like radically different from kind of classical dual decomposition approaches there. So I don't know if there's anything more interesting I could say about that, but that's a thing that you can do.
Okay, thanks.
Great talk. So I was curious about the kind of meta loss function, namely this kind of double derivative application.
Mm-hmm.
Like, does it require computing the Hessian? And if so, how do you make it fast?
What was the second part?
If so, if it requires computing the Hessian, how do you make that fast? So
I
that
see.
you can actually
So it doesn't require computing a Hessian. It does require computing a second derivative, but but you never actually build the full Hessian matrix. It turns out that if you set up your automatic differentiation properly, the cost of that second derivative is not actually that much more than the cost of the first derivative. So it goes up, but it goes up by a constant factor. So yes, it is more expensive, but not like going from end to end squared.
Thanks.
Thank you.